Today's lesson is about conditional probability. We've learned a bit about conditional probability in the past, but we're going to dig a little bit deeper into it today. But before we get started on that, let's go ahead and take a deep breath. And we'll go ahead and get started. So the first thing I'd like to do is I'd like to remind you about what our notation was for conditional probability. Remember that we use sort of this vertical line here. This is read the probability of A given B, and it represents a probability of A happening. So this is still ultimately about A happening, but it's conditional on B sort of being something that we already know. Okay? In one of those previous lessons, we learned a formula. We learned that you can find the probability of two events, A and B, by multiplying the probability of one of them by the conditional probability of the other one of them. And what we're going to get into today is effectively a modification of that formula. If I were to take this and simply divide the probability of A over to the other side, we would wind up with this, which is the formula for conditional probability. You'll find this formula in the IB formula book, and just in general, it's the formula for conditional probability. I do want to point out that these two things could also be the other way around. You could have the probability of A given B as well, and the only difference is that the probability in the denominator would be the probability of B. So it's kind of like whatever this given probability is, that's going to be the probability that's in the denominator. And the numerator is just going to be the and probability of the two things that you have inside. So for instance, if you wanted to do the probability of M given N, you might want to pause the video for a moment and make sure that you can figure out what this would be. In the bottom, you'd have the probability of N, and in the numerator, you'd have the probability of M and N. Keep in mind, this thing up on the top could also have been N and M. That doesn't really make a difference because it's a commutative thing. The order doesn't matter. Now, I'm glad that we have this formula. It's really useful. We're going to use it sometimes, but as you likely know, I'm really not a huge fan of us just memorizing and plugging numbers into formulas. I want us to have some sense of how this works, and so we're going to look into a simple example next to sort of see the formula in action, get a sense for how it works, and then we'll practice with it some more. So here's this simple example. Let's say that you roll a fair six-sided die, and I ask you to find the probability that you roll a prime number given that your roll was odd. And I'd really kind of like to do this problem two ways. I'd like to do it just sort of thinking about it, and then I'd like to use the formula and show you that we get the same thing. Now, to be fair, just because you're using the formula doesn't mean that you're not being logical. These aren't opposites of one another, but they are sort of different ways of approaching the problem. So if you were going to think logically about this, you might think, well, if I'm rolling a fair six-sided die, there are six outcomes, right? There's 1, 2, 3, 4, 5, and 6. And then the problem says, find the probability that you roll a prime number given that your roll was odd. Well, given that it was odd, it sounds like there weren't really six options. There were really only three options. Given that I rolled one of these, what's the probability that I rolled a prime number? Well, of these ones, 3 and 5 are the prime numbers, so it looks like there's a 2 out of 3 chance that I get a prime number given that it was odd. Okay? That's us sort of thinking logically about it. Right? When they said given that the roll was odd, it sort of restricted what I was going to be able to look at, and so this is what I came up with. Now let's take a look at it using the formula, right? What we're being asked to find here is we're being asked to find the probability of prime given odd. I'd like you to pause the video here for a moment and write down what sort of the next, what would our formula tell us that we need to do here? Well, according to the previous page, what we talked about, in the top I would have the probability of prime and odd. You might have used the intersection notation there. In the denominator, we would have the probability of odd. Now let's see what these probabilities are. The probability being prime and odd, well, let's see here. In the numbers 1, 2, 3, 4, 5, and 6, prime and odd is 3 and 5, so that would be 2 out of 6. And the probability of odd, that would be 1, 3, or 5, so that would be 3 out of 6. And sure enough, that reduces down to 2/3. So you can see that we sort of get the same answer either way. And it's good for us to know that we can think about this logically. There's another way that we can think about this even more deeply, and that's what we're going to get into next. So there's this thing that I always say when I teach conditional probability, and if we were together physically in class, you'd hear me say this a lot. And it's this idea. It's this idea that when we find conditional probability, I want you to always be thinking about how you are restricting the sample space to the condition. Think about in that previous problem that we did when we knew that we had rolled an odd number and we restricted our sample space to being just 1, 3, and 5. We said, 2, 4, and 6, we know those didn't happen because we knew it was an odd number. That's the idea here. Anytime anybody ever asks you for a conditional probability, I want you to think about how you are restricting the sample space to the condition. And we're going to come back to that idea a lot as we talk about conditional probability. So I have an example here, and I want to sort of show you how a Venn diagram can actually help you to think about this idea of restricting the sample space. Okay, so I want us to consider events I and B such that the probability of I is 0.5, the probability of B is 0.3, and the probability of the intersection is 0.2, and then I'm going to ask you to find the two different conditional probabilities. Okay, so let's start by drawing a Venn diagram. Okay, so here's my Venn diagram, right? And over here I'm going to have the event I, over here I'm going to have the event B, and we're told that the probability of I is 0.5. So this entire circle is 0.5. So you guys know I like to write the 0.5 out here. And then probability of B, this other circle, this entire circle then has to be 0.3. Okay, and then we're told that the intersection is 0.2. Okay, so that means that this part here is 0.2. So given that, how much is this crescent then? If the whole thing is 0.5 and the middle part is 0.2, it means this part here has to be 0.3. And similarly, this crescent of B alone over here has to be 0.1. Okay? Now, I'd like to do sort of a similar thing where let's look at the probability of I given B. And I want us again to sort of think about this logically, and then we'll also look at it in the lens of the formula. So if I were to sort of think about this thing logically, I would think about it and say, well, all right, let's start by restricting ourselves to the sample space. This thing says given that B has happened. So given that B has happened means that I am existing in this space. This circle here is the entire universe as far as this problem is concerned. So my sample space, my denominator, is going to be 0.3. Okay, now within that universe, within that B space, where does it happen that I happens? It wouldn't be the entire circle because I'm only getting to look at within this. Within this circle, I only happens right here. It happens in the intersection. So I would put 0.2 on top and I would wind up getting 2/3. It's totally coincidental, by the way, that that's the same answer we got on the previous page. That was us sort of thinking about this logically, thinking about this as a restriction of the sample space. Right? What would it look like for us to do this with the formula? Well, you're going to find it's really similar. It would be the probability of the intersection on top over the probability of the condition on the bottom. And it's literally what we just did. It would be 0.2 for the intersection, 0.3 for this, which reduces to 2/3. So I'd like you guys to pause the video now, go through and find the probability of B given I, and make sure you can do that on your own before we go on to the next thing. Okay, so the probability of B given I, again, for me, I really like to think about this in terms of what I can see and what I can understand. I think about this as I'm going to restrict myself to the sample space that's just the condition, which means 0.5. And then in the numerator, I need to figure out within that space, within this I circle, when does B happen? That's again going to be the intersection, so 0.2. So this other conditional probability is 2/5. I don't know how many times I've said it on the slide so far, but I'm going to say it one more time. When you're finding a conditional probability, I want you to think of it as a restricting yourself to the sample space of the condition. All right, so I've got one more slightly more complicated example here of a problem that uses just notation, and then we're going to get into sort of word problems. So go ahead and pause the video and try working your way through this one. I'm going to remind you guys that just because we have a new formula doesn't mean that the old ones are obsolete. You may still find that you're going to need to use some of those old formulas, so keep that in mind. All right, so let's see here. The problem gives us the probability of A and B and a union, and they ask us for the intersection. That reminds me a lot of one of those first formulas we learned, that the probability of the union is equal to the probability of the first event plus the second event minus the probability of the intersection. So it seems pretty clear to me that we can just plug numbers into this thing. Our union was 0.6, the A was 0.4, the B was 0.3, and the intersection is the thing that I want to find out. Okay? I'm going to skip a little bit of step here, but I hope you guys can find pretty easily here that if I move some things around, the probability of the intersection is 0.1. Okay? Now part B asks us to show that these events are not independent. Okay? Now I might say something here that, remember, what does it mean if they're independent? Okay? If they're independent, it would mean that the probability of A times the probability of B would be the intersection. So let's go and check that out. The probability of A times the probability of B, these were both given to us in the problem. This would be 0.4 times 0.3, and those two things multiply together to be 0.12. These two things aren't the same, right? Therefore, A and B are not independent. Now, part C of the question asks, okay, great, so find the probability of A given B. And I want to mention really briefly why part B in this problem even existed. Because here's the thing. If they were independent, what would the probability of A given B be? Like, think back to some of our lessons in the past. If A and B are independent, it means that B has no impact on A, which means the probability of A given B would just be the probability of A. Okay? But we just showed that they're not independent, which means this is not true, which means, okay, I actually need to find the probability of A given B. Okay? In other words, if we hadn't done part B, if they were independent, we would already be done with the problem. We'd already know the probabilities of A and B. Okay? I hope that wasn't confusing. So they're asking us now to find these two conditional probabilities. I'm going to ask you guys, pause the video, try these on your own, make sure that you can do them. The probability of A given B should be the probability of the intersection divided by, remember we restrict ourselves to the sample space of the condition, the probability of B. So let's see, the intersection here was 0.1, and the B probability was 0.3, so this is 1/3. Similarly, the probability of B given A would be the intersection, which again was 0.1, divided by restricting to the sample space of the condition, 0.4, which is 1/4. So using the key point that we talked about before, and thinking about Venn diagrams and thinking about restricting ourselves to the sample space of the condition, these problems are usually pretty straightforward when they're posed using unambiguous mathematical notation. But when we're doing word problems, when we have the complexities of the English language, it can sometimes be tricky to understand what the question's asking for. And so I want us to sort of practice reading these 5 questions and making sure that you guys can write down what the notation is for them. I want you guys to recognize, by the way, we have multiple notations for probability. We have an and probability, we have an or probability, and we also have our conditional probabilities, and there's 2 different ways that those can go. There's A given B and there's B given A. Added on top of that, we also have our complement notation, our not notation. And so, like, all of these things could show up in this. So go ahead and make your 2 events for these, French and biology. So you could call them F and B if you'd like. But go ahead and pause the video and try these out. If you want to do them one at a time, that's fine, or you can try all of them. As you're going through these, I want you to think about, is there a condition here? And if there isn't, is it and or? How do we work through this? So this first one, it says a student is studying French, period. What is the probability that they are also studying biology? I hope it's fairly clear. In this one, it just straight out says a student is studying French. In other words, we know that this student is studying French. This is going to be the probability, and then it says what is the probability they're studying biology? This is going to be the probability of bio given French. Okay? And now that I have that, we could apply our formula to that. The new formula that we just learned would apply to this. We can use that. It would be the probability of the intersection divided by the restriction to the sample space. Let's go on to the other ones. What is the probability that a student studies both biology and French? In this one, there's no assumption being made. The assumption is that it's a student, but that's not either of my events. Right? So the probability that the student studies both biology and French, this would be the probability of bio and French. Okay. Next one, what proportion of biology students study French? Does this problem have a condition in it? Is there some prior assumption being made here? And there is. It says, what proportion of biology students? Okay? In other words, it's almost like you're walking into a bio class, you're looking at the bio students that are there, and you're saying, hey, raise your hand if you're studying French, right? So what proportion of biology students study French? This would be the probability of French given bio. I know that one can be a little bit confusing, so if you need to, like, pause the video, rewind, listen to that again, make sure that you're understanding why bio is a condition here. This fourth one is arguably one of the most confusing ones just because of the way that English is structured. So I hope you guys got it right. If not, let's think through what it would mean. What's the probability the student studies neither French nor biology? Think about what that means. This means this person is not studying French and they're not studying biology. This would be the probability of not French and not biology. You don't want to say not French or not biology because that means that they're not taking one of those things, right? We need them to be doing neither one of them. Okay? And then the last one, what is the probability that a student studying French is also studying biology? Does this problem have a condition? And it does. It says, what is the probability that a student studying French, this is our condition, what is the probability that they are also studying biology? So this would be the probability of studying biology given that they are studying French. Okay? And notice, it was the same thing for the first and the last one here, but they were worded differently. There are different ways that we can ask the same question in English, and so you guys need to make sure that you can sort of convert that and understand what's being asked of you in math language. So I have here an example of a problem that's going to sort of go through some of this conditional probability and a variety of these, using the English language. You guys have probably noticed that I'm a really big fan of using diagrams and charts for these problems and for thinking about probability in general, and that's going to be no difference here. It says a high school class has 63 IB diploma candidates. Of these, 44 are studying biology, 25 are studying math HL, and 15 are studying both. This really sounds like a perfect setup for a Venn diagram. So I'd like to just represent all of this on a Venn diagram just so that I can see what's happening, right? So I've got this Venn diagram. I understand that the entire thing is 63, right? So this whole thing is going to be out of 63. I'm going to have a bio circle over here and a math circle over here. There's supposed to be 44 things inside of the bio circle. There's supposed to be 25 things inside of the math circle, which means there's 15 of them that are in both. Okay. Now that I've got that, I can sort of fill in, honestly, the rest of this Venn diagram. This crescent has to be 10. This crescent over here has to be 29. Now, if I add all of these things together, I'm going to have 25, 54, so it looks like 9 total out here. Now that I have a diagram set up for this, I can go about answering questions. Right? Question A, find the probability that a student studies biology or math HL. There's no conditions here. This is just the probability of bio or math HL. Okay? Well, let's see here. Bio or math HL, that would be this entire thing, right? Well, that entire thing, there are 54 things that are in that union out of 63 that are in the overall space, and so this can be our probability. I suppose this could be reduced. This could be 6/7. Part B, find the proportion of math HL students who are studying biology. So think for a moment about what this is. How would I write this with notation? The probability of math HL students who are studying biology. I would find this out by going into a math HL class and asking students to raise their hand who are taking biology. Okay? So to do this, I am going to be restricting my sample space to math HL students. So math HL students. So that means my denominator is going to be 25. Okay, and of those 25, how many are taking biology? That's the intersection right here. Right? So this problem was basically the probability of bio given math HL. So if we wanted to use the formula here, I would have put the probability of math on the bottom, restricting myself to the sample space of the condition, and in the numerator, I would have put bio and math. So if you're really committed to using the formula, that's what it would look like. But I want to point out to you guys that if you have a diagram, you're allowed to use that diagram to break these things down. So this reduces down to 3/5. Let's go on to our last one here, part C. What is the probability that a biology student is studying math HL? This looks like it's just the other way around. This is the probability of math given bio. So again, if you want to use the formula, you restrict yourself to the sample space of the condition, and in the numerator you do the intersection. Okay. As far as I'm concerned, though, I can just look at this and say, well, given that they did bio, that means this is my world, this is everything. So my denominator is 44. And in the numerator, I put the ones that did math, that would be 15. So I hope that all made sense. I think at the end of the video, the thing I want to say is the thing that I've said like 20 times in this video. When you're doing conditional probability, always think about restricting your sample space to the condition.